In your high school, you might have been forced to learn a rule where the derivatives of x to the power n can be obtained by making the power hop in front, leaving one behind. But that's just an easy way to memorize, but not a good way to understand. Hey guys, this is the High School Scientist, and in this video I'll be explaining the basic concepts of calculus and as well as help you build an intuition about this topic. But first things first, we have to understand what a derivative is and why the formulas of calculus work the way they work. So I think of calculus as a tool, in fact a very important tool, which makes really hard and confusing concepts easy enough to understand. Like for example this statement, velocity at an instance, makes absolutely no literal sense because velocity itself requires time to change. When someone says velocity, they generally mean the movement of an object with some difference in time. But this phrase, velocity at an instance, seems so absurd that it feels like it's been created to confuse people. And this is where calculus lets us know how helpful it can be. So I'll first try to explain it with some examples, and then we can talk about velocities and rate of change of different things. So here we have a square whose sides have a length of 4 units. So now the area of this square should be 4 square. Okay, but what if I change this length with a very small value? Like let's say I have increased the length to 4.001. Now this tiny change will cause the entire area of the square to change. Even though it's a very tiny change, still the area changes by a tiny amount. And this is where we start to understand differentiation. How much does the answer change if I change the question? So in this example, when we check the ratio between the change caused by me with the total change in area, we find the ratio to be approximately 8 units. To better understand this, we may have to take a mathematical approach. So here you can consider the length to be x and delta x as a slight change in x. The total area would be y, which basically means it's x square. So now the total change in area would be the sum of these two pieces and a tiny square. The area of the first piece is dx times x. Once again, d is nothing but a way to represent a very tiny change in x, which is meant to approach 0. The area of the second piece is dx times dx, and the area of the third piece is x times dx. So here we have to find the ratio between the change occurred and the change caused. And that's why we divide the entire thing with dx. But note that these figures are much smaller than they appear. I'm showing this just because for you to understand the concept, but in reality, these are really small. Okay, but now when we simplify this, dy by dx, we know that the second piece of area is really tiny. For example, if dx were 0.001, then the area of the dx square would be 0.00001. It is safe to neglect it from the equation, and after simplification we get 2x, and that's the derivation of x square. In your high school, you might have been forced to learn a rule where the derivatives of x to the power n can be obtained by making the power hop in front, leaving one behind. But that's just an easy way to memorize, but not a good way to understand. The way I want you guys to understand is what happens when dx approaches 0. So in this example, which I just explained, also works for powers greater than 2 or any other number you like. Okay, for instance, we have to find the derivative of x cubed, And we can imagine that this x cube is some kind of a cube with a side length of x. So now, according to the definition of a derivative, we have to know the ratio between how much will the entire cube change by the tiny change caused by me. And also remember that we are making this change approach 0. I'm not asking you to imagine anything related to infinity, but just something really small which is not 0. And if you notice, the majority of the change comes from these three sides and not from the edges and corners. And now if we calculate the ratio, then we find something interesting. Here the terms 3x squared times dx is the volume of these three expanded surfaces. 3x times dx squared is the volume of these edges, and the term dx cube is the volume of this tiny corner. And the trick that calculus wants us to understand is what happens when this dx approaches 0. And let me remind you again that this is nothing to do with dx being infinitely small. Infinity is not a factor in differentiation. So with that said, and now after looking at the third equation, we know that dx square is going to be really small, and dx cube will be even smaller. But both of them get even smaller when they approach 0. So all I'm trying to say is we can safely remove them from the equation. But this 3x square times dx is important. It's important to us so that we can get rid of the denominator. And hence the derivative of x cube is 3x square. And this method is true even for x to the power 4, x to the power 5, x to the power 7 or x to the power 11 or any other number for that fact. Because at the end, when we make dx approach 0, all of them disappear, leaving 1 behind. And this is all I want you to understand. Now that you do, it would naturally raise a question to know where to apply this. And now would be the right time to take a look at this term, velocity at an instance. So let's draw a graph which shows the distance traveled by the car over a period of time. So the x-axis would be the time and the y-axis would be the distance traveled by the car. And this graph is represented as a function. So all we have to do to find the velocity at an instance is to change the value of x by a very small amount. And this would cause y to change by a very small amount. The ratio of change caused to the ratio of change occurred will give us the velocity at that point, but only when we make this change approach 0. Basically, the slope at a point and velocity at an instance are mathematically the same thing. So I hope that this example made it simple enough for you to understand differentiation, and if it did, then just spread the word, let your friends and classmates know about this channel. This is the High School Scientist signing off.